Hello again, physics fans. My name is Varun Yarabarla. This is my video report on Lab 4, the Rope Physics Spring Mass Lab. The point of this lab is to quantify the motion of a mass attached to a spring and tracker using a video provided, and through the application of Newton's second law and the energy principle, the motion was predicted and analyzed through VIDLE. Once this was done, a comparison had to be made between the predicted motion from the model and the actual data extracted from tracker. The motion of the mass was similar for both in the x and the y directions. The results were that the predicted motion of the mass followed the same pattern as the data received from tracker. The spring mass system does indeed satisfy the energy principle. The two main principles that are applicable to this lab are Newton's second law and the energy principle, as these are the two models relevant to the physical system. The momentum principle helps predict the spring's new velocity and its position. The energy principle is the total energy of the system, which is equal to the kinetic energy plus the gravitational potential energy plus the spring potential energy. Once the video was in tracker, I placed a calibration stick so that it represented the spring's relaxed length at 0.7 meters. I put the origin at the point where the spring was attached, and after pinpointing all the point mass locations, I took the x and y positions shown here on the right and placed them into a CSV file that could be used into my code. The x and y positions are placed in the A and B columns here. In this part of the code, all the initial conditions are shown, such as the mass of the ball, which is 0.42 kilograms. The initial position is shown here. The initial velocity is 0 meters per second, and the start time was at 0 seconds. All the position values that were extracted and placed into the CSV file are read into the code here. The other initialized values include the time step, which was provided, and the gravitational constant g, which is 9.8 meters per second. Next, I used the equations here on the left to solve for the spring constant, the change in stretch, and the stretch length of the spring. Then I put each of these values into my code, as you can see here. Using the formulas for omega and period, I solved for the spring constant, which came out to be 6.88 newtons. L initial is the spring's relaxed length and was solved to be 0.128 meters. This is the code that calculates the length of the spring at each time interval. L hat is the spring's direction. S describes the stretch or the compression, and it is used to compute the spring force and the spring energy. Now for the system's energies. The energies that are present in the system are the kinetic energy, gravitational potential energy, and the spring potential energy. These are calculated using the equations shown here on the left of the screen. Here, I calculate the initial energies and set them equal to these variables that are used later on. The values of these variables change as the system moves. Here's the gravitational force with mg in the negative y direction. F spring is just Hooke's law. F net is the sum of the gravitational force and the spring force. This F net value was used in Newton's second law, shown here, to predict the new velocity of the spring system. The position is then updated when the velocity changes at each time interval. Then, the spring is updated in this portion of the code. The position of the spring changes, so does the stretch and the compression. These lines make the spring move and updates the visual model. The last thing that is updated is the new energy of the system at each time interval. The kinetic energy, the gravitational potential energy, and the spring potential energy change and have to be recalculated to update the proper values. Changes in these energies are then stored and plotted to notice the energy change at each time interval. Now you can see the model in Python. The red ball is representative of the data from tracker and the blue is of the computational model. It is clear that they are following the same path. They are very close to each other. The blue arrow is the spring force and the black arrow is the gravitational force. The graph on the right shows the position data in the y direction. It is very close, so my computational model does a good job predicting the original motion of the mass. The reason for the slight discrepancy between the two lines is due to the fact that the drag force catches up with the spring and there is some slight round-off error. I also made a graph that shows all the energies in the system. The graph shows the different energies. Here, the blue line is the change in kinetic energy, the red line is the change in spring potential energy, and the green is the change in gravitational potential energy. The yellow is the sum or total energy of the system, which is 0. Now let's answer the questions. Question 1. The work done by the surroundings is equal to the change in energy, but because there is nothing in the surroundings with the Earth, spring, and mass being the system, then the work, by extent the change in energy, should be 0. There is no outside work done on the system, so W equals delta E. Delta E on the graph shown here is 0, which does make sense. Question 2. These are the two oscillation graphs. The period of oscillation for x is 1.7 seconds, and for y it is 1.52 seconds. It is clear that the x and y oscillations differ by 0.189 seconds. This is because, as seen here, the motion of the spring is elliptically shaped and slanted downwards. The figure on the right explains this a little better. This shows that it takes more time to move one cycle in the x direction than in the y direction.